Hey guys, today we're going to take a look at section 4.2 exponential functions. Okay, so we've covered a lot of different functions this year, right? We did quadratics, square roots, cubics, absolute value. Okay, so hopefully you haven't forgotten all those. And what we're going to do today is we're going to add on to that list. Okay, so what is an exponential function? An exponential function is a function that's in the form of a to the x power here. Okay, now a is the base and x is the exponent. Okay, now x is the exponent, x is also our variable. Okay, a is the base here, we're using a letter for it, but the base is always going to be a constant value. Okay, so some examples of some exponential functions, right? F of x equals 8 to the x power. Don't want to use f again. Let's use g. G of x equals, let's go 2 to the 3x power. Right? Base is constant. The variable is up in the exponent. Let's do one more. H of x equals 3/4. I'm going to put that in parentheses to the x power. And we'll look at one with a fraction here in a second. Okay? Now, if a, the base, is greater than 1. So looking at things like f of x and g of x here, okay? And now m is less than n. Therefore, a to the m will be less than a to the n, okay? And so, what does this mean? All right, basically what we're looking at here is, I'm going to go ahead and erase these second two examples here, and let's just look at f of x. Right? If I look at f of 2 compared to f of 3, right? Well, 2 is less than 3, right? So if I look at 8 squared compared to 8 cubed, right? Obviously, 8 squared is going to be less than 8 to the third power, right? 8 squared is 64. 8 cubed is a number larger than 64. 512, I think? Something like that? Somebody double check me. Okay, so that's what this sentence means here. Okay, base is greater than 1, right? When you input a value, whichever one has the bigger x is going to have the bigger output. Okay? Now, similarly, if a is between 0 and 1, okay, let's erase f here. I'm going to bring that example for h back. H was 3/4 to the x power. Now, for this one, let's look at h of 1. What's 3/4 to the first power? Which is just 3/4. And now let's compare this to h of 2, which is 3/4 squared, which is going to be 9/16. Now, for something like this, the x value that's smaller actually gives us the bigger output, right? 3/4 is 0.75, right? And 9/16 is somewhere closer to 0.5, right? Because 8/16 is a half. So this is really close to that. Okay? So even when x is bigger here, right? And when the base is between 0 and 1, the output is actually going to be a smaller value. Okay? And so we're going to put words to these coming up in a little bit. Okay? But before we do that, let's go ahead and look at some graphs. I'm going to erase h here. We don't need this anymore. Okay, so my favorite thing to do, okay, let's look at some graphs. Here we have a function, 2 to the x. Okay, f of x equals 2 to the x power. Alright, so best way to graph a function, right, you can always make a table, right? You can always take x values, plug them in, okay, and see what the outputs are. Now, I'm going to start with 0 here, okay? What is f of 0 going to be? Well, f of 0 is going to be 2 to the 0 power, and hopefully we remember that anything to the 0 power, well, any positive number to the 0 power is going to be 1. F of 1, 2 to the first power is 2. F of 2, 2 squared is going to be 4. F of 3, 2 to the third power is 8. Okay? So the positive numbers and 0, right, those aren't too difficult. Now, let's look at the negatives, okay? F of negative 1, well, that's 2 to the negative first power. Now, hopefully we remember that a negative exponent just means to take the reciprocal. So this is going to be 1/2. And then 2 to the negative second is going to be the reciprocal of 2 squared, which is going to be 1/4. Okay? So let's plot these points and see what we have. Okay, so the first thing we got is 0, 1. Okay, 1, 2. 2, 4. And 3, 8 should fit right at the top. Then we have -1 and 1/2. Then we have -2 1/4, and we're getting really close down there. Okay, so we can kind of see, right? We can kind of see the shape forming here. Okay, so I'm going to go ahead and connect the dots here. Like that, and like that. Okay, so one smooth curve here, right? Looks like it's going to keep on getting bigger as x gets bigger, and it looks like it's going to keep on getting smaller. Okay, and we'll talk about what's happening here as x gets more and more negative. Okay, now let's do the same thing for 1/2 to the x. Okay, so for 1/2 to the x here, okay, this time I'm going to work a little bit different. I'm still going to start with 0, right? 1/2 to the 0 power is still going to be 1. I'm actually going to plot this as I fill in the table. Might go a little bit quicker here. Let's do -1 now, right? 1/2 to the -1 is going to be the reciprocal of 1/2, which is going to be 2. Plug in -2. 1/2 to the -2nd power is the reciprocal of 1/4, which is 4. One-half to the -3rd power is going to be 8. Okay, now let's look at the positive values here. Plug in 1, I get 1/2. Okay, plug in 2, I get 1/4. Points should look very familiar. And let's connect the dots. That is a crappy curve. That's how you do it, folks. That's how you do it. Okay, so let's just take a look here real quick. Let's see if we can compare these two graphs at the same time, right? 2 to the x, right, as x gets bigger, the graph gets bigger. 1/2 to the x, as x gets bigger, the graph gets smaller and smaller, right? And we can also kind of see, right, these two graphs are just reflections of each other over the y-axis. Okay, now this is going to be true for any bases that are reciprocals of each other. Okay. So here are the basic shapes for an exponential function. All right, now let's see what we can summarize from here. Okay, general properties of the exponential function. Okay, there's 3 points you can always identify on the graph. Okay, most importantly is the middle one there, 0, 1. Okay, and now whatever your base is, right, a to the first power will always get you a, and then a to the negative first power will always get you the reciprocal. Okay, you can always find those 3 points relatively quickly. Now, we kind of hinted at this earlier, okay, but if a is greater than 1, right, then we say that f is an increasing function. Okay, right, the graph constantly kept getting larger and larger, right, it curved upwards. And if a was between 0 and 1, okay, then we had a decreasing function, right? The values just kept getting smaller and smaller and smaller, right, as x got bigger. Okay, now, how small did they get, right? Let's take a look back at the graphs here. Okay, for both of these graphs, they kept getting closer and closer and closer to 0. Okay, however, they will never actually reach 0. Think about it, right? Can you take 2 to some exponent, which I'll represent with this box here, and get 0 for an answer, right? There is no such answer, right? This will never equal 0, ever. And therefore, we get that the x-axis is a horizontal asymptote for an exponential function. And then two other small things here, right? Domain, all reals, negative infinity to infinity, right? We can plug in any x value in, and we should be able to evaluate it as an exponent, okay? And the range, what we just talked about, will never reach 0, right? And then on both of the graphs we did, no matter what a was, right, there was always a portion of it still going up to infinity, okay? So the range is parentheses 0, right? 0 is not included, all the way up to infinity. Okay? So we'll be doing more with graphing of these in the relative future. Okay, but here are the properties that you need to know. Okay, moving on. Last thing we're going to look at here with exponential functions is actually looking at some exponential equations, okay? Actually, specifically the first two here. The last one is actually not quite an exponential. We'll talk about that last one in a moment here, okay? But let's look at problems like the first two here, okay? 1/2 to the x equals 32. All right? Now, we're solving for x here. Our variable is inside the exponent, okay? Now, the best thing to do here is to think about the exponent on the other side, right? Currently, this is 32 to the first power. Now, let's say, I'm going to give you, actually, you know what? I'm going to give you a different problem, okay? If I told you I had 3 to the x, and that was equal to 3 squared, right? I think it's pretty safe that you guys would say that x had to equal 2, right? When the bases are the same on both sides of an equation here, right, the exponents also have to be the same. Okay? So let's apply this logic to the problem we have at hand. Okay? 1/2 to the x power equals 32 to the first power. Can I think of a common base for both of these? Or in other words, how can I rewrite 1/2 and 32 so that they have the same base raised to some other exponent? Okay? Now, some of you guys might be able to take a look at this and figure it out, but if you can't, right, the common base here is actually going to be 2. Okay, now there are other possibilities, okay, but 2 here is going to work pretty well because 1/2 is the same thing as 2 to the negative first power. And now that's raised to the x, and this is going to equal, now 32, you might have to do a little bit of mental math here, powers of 2, 2, 4, 8, 16, 32 is 2 to the 5th power. And now that's raised to the first. And now, hopefully, we remember some properties of exponents, right? Exponent raised to an exponent means you're going to multiply, so I get 2 to the negative x equals 2 to the 5th, right? And now, we just talked about this, bases are the same on both sides, therefore, your exponents have to be equal. Negative x equals 5, therefore, x is equal to negative 5. And that is our final answer. Okay. Now, let's take a look at this next one. Okay, this one might be a little bit easier because, again, look at your two numbers here, 3 and 27, right? What should the common base be here? Think about some exponents that you know, right? Think about 3 to the first, 3 squared, 3 cubed. Well, 27, I hope we don't have 27 squared, 27 cubed memorized. Okay? But here, common base of 3 is going to work. Okay? So, let's leave the left-hand side alone. And the right-hand side, 27, is the same thing as 3 to the third. Okay? Left-hand side, again, keep that the same. Right-hand side, now, you're multiplying an exponent with another exponent, except here, be careful, you have to distribute 3. Common mistake, people forget to distribute, and that's going to give you an incorrect answer. So this is going to be 3x minus 18. Oops, sorry, 3 to the 3x minus 18 to the power. And now, bases are the same, so exponents have to be equal. Therefore, x plus 4 equals 3x minus 18. Now I'm going to give you guys a little bit of credit here and assume we can solve a linear equation. And you should get x equals 11. Alright, one more to look at here, okay? Again, I think I mentioned this before. This last one here is not an exponential equation. X to the 4/3 power equals 81, okay? Now, I'm going to do this problem, or actually, sorry, I'm going to give you a little clue on how to do this problem, okay? Let me give you one that's similar to it. X squared equals 81. Now, you're solving a quadratic equation here. What would you do to both sides? You take the square root, you take the square root. Left-hand side gives you x, right-hand side gives you 9. Now, the only difference here is, since you're solving a quadratic equation, you have to put a plus or minus with it, giving you 2 answers. Okay? It's the same concept here with x to the 4/3. Your goal is to undo the exponent. Just like squaring undoes undoes the square here, right? Square root and square are inverses. Hey, there's that word we just learned a couple days ago, right? Those are going to undo each other. You're going to want to do the same thing here, okay? X to the 4/3 equals 81, okay? Your goal is to undo that exponent. I'm going to rewrite the problem down here at the bottom. Give us a little bit more room. X to the 4/3 equals 81. Okay, so what exponent would undo 4/3? How about 3/4, right? Because now on the left-hand side, I would multiply those two. 4/3 times 3/4 is going to be 12 over 12, which is 1, which is just x to the first, which is just x. And now on this side, I have 81 to the 3/4. Now, there's 2 ways to evaluate this, right? The better way is to do 81 to the 1/4 power and then cube that, because 81 to the 1/4, what's the 4th root of 81? Or in other words, what number to the 4th power gives you 81? And hopefully a lot of you there are saying 3. And so now x equals 3 to the 3rd power, which is 27. Except this is x to the 4/3 power, right? What if I let x be negative 27? Well, if I took negative 27, took it to the 4th power, that would give me a positive number whose cube root would still be 81. So in this case, I have 2 answers, plus or minus 27. Okay? It's only when you have an even number in the denominator is where you have to be careful about plus or minuses. Okay? Here, I can take negative 27, plug it in, and still get a positive number. Okay? So I do get plus or minus 27. All right. Okay, that's all we got today for exponential functions. All right. Nicely done, and I will see you guys soon.